Hello, everybody, and welcome to your 21st lecture in Earth Science. This is Dr. Hurt. We're continuing our march along with the learning about the atmosphere, weather, and precipitation, all those good things. So we did the atmosphere last time, and now we are continuing along doing moisture, clouds, and precipitation. This picture that you see here before you is from Tampa Bay. Tampa Bay, Florida, is the leader in the nation in thunderstorms. So we have the most thunderstorms there, almost on average one per day there in Tampa Bay. So anyway, we're going to be talking about how thunderstorms develop and how rain and clouds and things like that all happen on Earth. So that's the goal for today. So, a lot of what we're going to be talking about is going to be focusing on water. And as you know, water comes in 3 different states, okay? And on Earth, we find it in those 3 different states. We, of course, have the solid state, which is ice, the liquid state, which is liquid water, of course, and water vapor, which is a gas. Now, this is, of course, we have solid precipitation. Solid H2O precipitation is snow and ice. Of course, you all know rain is the liquid form. And we also have water as a gas. Now, this is a little bit misleading. Fog is actually not a gas. Believe it or not, fog and clouds. Fog is, by the way, just a low-lying cloud on the ground. Fog is actually composed of microscopic water droplets. So clouds and fog, they are not gases. They are liquids. It's just microscopic droplets of that liquid, okay? So it's a little bit misleading, but I kind of show it just to represent H2O in a gas form, because you actually cannot see H2O when it's a gas. It's an invisible gas, okay? So you don't actually see, in reality, you don't actually see steam. What you see, for example, when you see a steamy pot or steamy kettle or something, you're actually just seeing the water condensing from a gas. That's what's actually visible to you. So whenever you see it, see like a cloud or steam or anything, that's actually liquid water, but it's just in microscopic droplets, so it's suspended in the air. Now, a very important concept here that we need to talk about, most of you probably never heard of this concept before, but it's called latent heat. Latent heat is the energy that is contained within the bonds between H2O molecules. Okay. Now, there's differing amounts of energy within the bonds of ice, differing amount of energy within the bonds between water molecules, and different amounts of energy in these bonds between all of the water molecules within a water vapor. Okay? They all have different amounts of energy. When there is a transformation from one state to the other, that energy is released or absorbed. Okay? It depends who has more energy in their bonds, So, for example, water has more energy in its bonds than ice does. So what this means is that when you melt, when there's melting, what's going to happen is there's going to be an absorption of energy, okay? Because water takes more energy than the ice does, okay? So there's going to be an absorption of outside energy. What this means is that melting, going from an ice to a liquid, is going to basically require energy. That means it's going to cool down. So this is a little bit weird, but I'm going to write this maybe in blue. Kind of makes a little bit more sense. It's going to cool down the atmosphere as it happens. So it's going to cool down the atmosphere around it because it requires more energy, more latent heat, to form water than it does with ice, okay? Furthermore, it's going to cool down a lot when we go from water to a water vapor, okay? So this is why, by the way, when you're running and you're doing exercise, you start to sweat, right? The reason that your body starts to sweat is to cool down, okay? And what it does is it precipitates water on your skin, and then the water evaporates, and when it evaporates, it takes energy, so it cools you down. It takes that energy, excess heat off of your body, off of your skin, okay? So that's that's the whole process. Extremely important process. You have to understand this because this has everything to do with how clouds form, how precipitation happens. It's extremely important. So you need to understand that when we go from an ice to liquid, there's melting. There's going to be a cooling effect on the atmosphere, a cooling effect on the surrounding environment. When we go from water to a water vapor, there's going to be a cooling effect on the environment, on the surroundings, okay? Vice versa. It's backwards when we go the other direction. So when we go from a vapor to liquid water, that's called condensation. Then we are actually going to be releasing heat. So this will be heating up. So going from a vapor to a liquid water is going to heat up the surroundings. Going from water to ice is actually going to heat up the surroundings. And I know that's really counterintuitive, right? Because think about that. Going from water to ice, freezing, is actually, believe it or not, heating up the surrounding a little bit. Now, it's just that the surroundings, when ice does form, that's usually the surroundings, the atmosphere, the land, the grass, everything is going to be usually cold. So we don't detect that heating up. But it's true, it actually does heat up when you freeze water, okay? It releases some energy, releases latent heat. So, by the way, there's some other kind of weird terms that probably a lot of people haven't heard of these before. When you go from ice directly skipping the liquid water phase to a vapor, that's called sublimation. You can see sublimation happening right here. This very cold ice is just going right into the vapor phase. Deposition, you can see this sometimes. Now, this doesn't happen too often in South Texas, but it does from time to time. Sometimes you'll see ice crystals form right on your car windshield in the middle of the night. That is deposition. That's when you go directly from water vapor in the atmosphere to an ice, right, to a solid. So that's an important process, and those things will come up as I move on through the lecture. So remember that water vapor, we do have up to 4% water vapor in the atmosphere, and it can vary anywhere between 0 to 4%, right? It's a variable component. That means a changing component of the atmosphere. Now, the atmosphere is only a little bit of the water of the total Earth, right? It's only 0.001% of the total water in the Earth, but there is water in the atmosphere. There's actually a good amount of water in the atmosphere. Water in the atmosphere can actually be picked up via infrared. You can actually, so you can't, remember I told you that water vapor is invisible to us, invisible in kind of normal light, the visible spectrum light, but actually, as a matter of fact, it can be picked up in infrared. So you can actually see water vapor in the air. You can see humidity in the air with infrared. Okay, it's kind of cool. So moving along, we have to talk about this idea of humidity. So humidity is just the concentration of water vapor in the air. It's how much water is in the air. And we have two types of humidity. We have specific humidity and relative humidity. So specific humidity is how much water is actually in the air in terms of grams of water vapor per kg of air. I know it's kind of weird to think about air being, how many kgs of air we have. Air has mass. It absolutely has mass. It absolutely can be measured, but it's just kind of difficult to do because it's buoyant. We can't put air obviously on a scale, but it does have mass, right? So we can talk about kgs of air. So specific humidity is just how many grams of water vapor is in 1 kg of air. Now, relative humidity is how much water is in the air divided by how much it could hold as a percentage. So it's specific humidity, how much water is in the air, divided by how much it could hold. Now, what does that mean? How much it could hold? So, at a certain point, air can only hold so much water. Okay? Think about, for example, you have a glass of water. I'm going to get maybe a blue pen out, draw our water. Okay? And there's my glass of water. I guess I have a red cup. And I'm going to get my spoon, and here's my spoon. Okay, and I'm going to fill up my spoon with salt. So there's my salt. Okay, it's my salt in the spoon. Now I'm going to dump this salt into my water. So if I dump some salt into the water, what's going to happen? So it's going to dissolve, right? It'll dissolve. But let's say I dump another scoop in, and another scoop in, and another scoop in. Okay, at a certain point, that salt is going to be just sink to the bottom, and it's not going to dissolve anymore. Okay, there's a limit to how much salt can be in water. Similarly, there is a certain amount of water that can fit into air. Okay, there's only so much water that can dissolve into air before the air is saturated. When the air is saturated, this is what happens. You get rain. Okay, you get precipitation. So once the air is so saturated with water, it has to come out as liquid water. Okay, so relative humidity is, again, how much water is actually in the air, so that's specific humidity, divided by how much it could theoretically hold. Now, this is how much, basically this curve that you see right here, okay, this curve is showing you how much water could fit in a kg of air, okay? It is a function of temperature. That's the thing. How much water can fit into the air depends on the temperature. At very high temperatures, so 120 degrees Fahrenheit, 50 degrees Celsius, we could have a lot of water in there. We could have up to 60 grams per kg, even more than that. Now at, let's say, kind of an average Corpus Christi temperature of 80 degrees, which is about, what, 26 degrees, 27 degrees Fahrenheit, Celsius, we can normally fit around maybe 25 grams per kg of water vapor in our air. And you notice that it goes up exponentially. So when it's 80 degrees, we can maybe get in 25 grams per kg. When it's 100 degrees Fahrenheit, so it's close to 40 degrees Celsius, now we're like way up here, right? Now we're almost getting close to 50. So it's kind of amazing, but it's like, it's 80 degrees compared to 100 degrees out, you can actually fit double the amount of water into the air. And that is why, you feel a big difference in the humidity level between 100 and 80 degrees. Like you can really, 100 degrees can really feel miserable. Why? Because you could put so much of that sticky hot air, water vapor into the air. So that's how it works. Now, if we have, let's say at 20 degrees, what is the maximum H2O content of the air? So let's look at here, 20 degrees. We follow this line up, circle right there, go over, and we see that it's about maybe like 15 grams per kg, right? So that is how much water that could possibly fit in there. So let's say that we had 10 grams per kg of water vapor in the air at the time, and it was 20 degrees Celsius. We could have 15, so the relative humidity would be 10 over 15, which is equal to what, I guess, 2/3, right? So that's equal to about 66%. Okay, so it would be the specific humidity. All right, let's talk about also a similarly related topic, which is the dew point. Dew point is so this is kind of a complicated sentence, so listen up carefully. So whatever you're doing, focus here and listen, because it's a complicated sentence. Dew point is the temperature at which air with a given specific humidity will start to precipitate. It will be saturated, okay? So it's the temperature at which water will start condensing from the air of a specific, with a specific humidity, a certain specific humidity, okay? So hot air can hold more moisture, cold air can hold less, but whatever the specific humidity is of that parcel of air, the temperature at which it'll start to precipitate out or condense out, that is the dew point, okay? So when air reaches the dew point, that's what it looks like. You get fog, you get clouds, you get precipitation. When a surface, like grass for instance, reaches the dew point, it will start to form dew droplets on the grass. So that's why when you go out in the morning when it's coldest, by the way, you know, usually the coldest part of the day is about 6 a.m., 5 a.m., right before the sun comes up, right? That's why you often go out around that time. It's cold and the ground is cold. It cools off faster than the surrounding air, and you start to get dew forming on the grass or on whatever surface it is. It's because it has reached the dew point. So if we look at specific humidity by latitude, you'll see that the wettest parts of the world are right there, kind of as you might predict, around the equator. Okay? You can see that the driest parts of the world are in the poles and mid-latitude, so it's relatively dry. Okay? Here in South Texas, we're kind of right there, right? So we have kind of medium specific humidity, but we're a lot lower. You know, we're here in South Texas, we're like about right here. You know, there are other parts near the equator, you're in the red zone, right? So it's like 3 times as much moisture as in the air. It's pretty shocking. Now, look at this same map in terms of relative humidity, okay? In terms of relative humidity, it's kind of vice versa. Around the equator, it's actually relatively low. The relative humidity is relatively low. Why is that? Because it's so hot around the equator, you could hold a lot of water, but there's not enough to saturate it. On the flip side, around the poles and the high latitudes is actually where the relative humidity is very high. Why? Because air can hold very, very little water at cold temperatures, okay? So that's the reason relative humidity is very high in the poles, but specific humidity is actually very low. So clouds form when a parcel of air reaches the dew point, okay? Clouds form, fog forms, dew forms, you know, it's basically all forms from the process of condensation, going from a vapor to a liquid. All that happens when a parcel of air reaches its dew point. Now again, what is the dew point? The dew point is the point of temperature at which air of a given specific humidity is 100% saturated with water. A dew point of 72 degrees Fahrenheit means that there's a lot of water in that air. So it's going to be hot, it's going to be sticky, it's going to be miserable. A dew point of negative 10 degrees Fahrenheit is going to look something more like this, okay? Means that the air is very, very dry. It's going to have to be extremely cold to get that little tiny bit of water out of the air, okay? So you can actually dew point's actually a pretty good measure. You can use dew point as kind of a measure of the humidity, okay, of a specific day. So if the humidity is high, your dew point will be high. So if anyone tells you the dew point is 75 degrees Fahrenheit, oh man, stay inside on that day. It's going to be sticky, hot, wet, horrible. A dew point of 50 degrees is usually kind of more comfortable for us, okay? So anyway, imagine the air has a specific humidity of 20 grams per kg of air. Okay, so I'm reading this right here. So what is the dew point at that given specific humidity? So the way that we can figure that out is we know that our air is 20 grams per kg. We follow to the curve, drop down, and we read the dew point right here. So it's about 25 degrees Celsius, okay? Or about maybe like 79 degrees Fahrenheit, okay? So pretty muggy, actually. Now, what if it's 10 degrees Celsius? What is the weather like? Well, if it's 15 degrees Celsius, what would the weather be like? So if it's 15 degrees Celsius, we would be right here. The dew point's 25 degrees C, so we're way below the dew point. So that means that if you're way below the dew point, what happens? If you're colder than the dew point, what happens? Dew, condensation, precipitation, rain. Okay, so remember, whenever the temperature goes below the dew point, that's when condensation occurs. Okay, I'm going to write that because it's so important. When you go below the dew point, that's when condensation happens. Whoops, I'm running out of space. Well, that's when condensation occurs, okay? So it's going to be rainy or foggy on that day. Here's a map showing typical dew points. Again, it's kind of a measure of what the humidity is like across the country. You can see that Corpus is right there, and just the worst place, you know, the most humid, right? Typical dew points are around 75 degrees Fahrenheit in August. Okay, it's pretty bad. This is for August, by the way. So August is almost like the very worst month here, I think, my opinion. But yeah, it's pretty sticky and uncomfortable, just as bad as in Louisiana and New Orleans area. It's pretty bad as it gets. So anyway, places that are in the west where we have the high deserts and things like that, you can see that humidity is very low there. All right, so fog and dew versus clouds. So fog, dew, clouds, they're all similar because they are all condensed water vapor, okay? All of that consists of condensed water vapor is just liquid water. But it should be clear that fog, dew, and clouds, it's all water. It's all liquid water, okay? So clouds are just liquid water that is in such kind of microscopic little droplets that it's suspended in the air, okay? So I think a lot of people, even my wife, you know, my wife has a master's degree and she didn't realize this. It's in philosophy, but she didn't realize this, that clouds are liquid water, okay? They're liquid water, they're absolutely liquid. It's just that the droplets are so fine and small, they're suspended in the atmosphere. Just like ash, you know? Like if you were to go and, you know, like take the ashes of a fire, it's very fine powder, throw them up into the air, they would float, right? Does that mean the ash is a gas? No, it doesn't mean it's a gas. It's solid. It's just, it's so fine that it can't overcome the air resistance to actually drop to the ground. Okay, another thing here. Fog. Fog is just a low-lying cloud. That's it. It's just a cloud that formed close to the ground. So if you ever want to know what it's like to be in a cloud, you've been in a cloud. Congratulations. You've been in a cloud. You've been in fog. You've been in a cloud. So it's the same thing. It's just close to the ground. Dew occurs when the surface of the ground could be anything, you know, could be your car, could be grass. A lot of times it's grass, could be the pavement, whatever it is. But it's just when the ground reaches the dew point, but the air surrounding the ground has not. And so you get condensation starting to form on the ground, on the grass or whatever it is. Okay. So whenever you cool down air, you always eventually you're going to get to the point that air starts to condense out water vapor. So condensation normally occurs through cooling a parcel of air to the given specific humidity. Okay, so if you ever want to know, how do I form a cloud? How do I form fog? How do I form dew? The answer is you have to cool a surface down. You have to cool down the air or whatever it is to a given, to the dew point. Okay, whatever the dew point is. And you reach 100% relative humidity. At the dew point, you're always at 100% relative humidity. And that's when condensation starts to occur, okay? So dew is just condensation of water vapor on the ground. Fog is just a cloud with its base at or near the ground, okay? But it's all liquid water. Very important sentence right here. So whatever you're doing, stop and pay attention. And you need to know this for the test and for everything in this class, okay? When air reaches its dew point, small droplets of water condense to form clouds, okay? So when air reaches the dew point, that's how you form a cloud, okay? That's how you get precipitation to occur as well. So clouds form when a parcel of air reaches the dew point. The dew point is the temperature. Again, what is the dew point? It's the temperature at which a parcel of air with a given humidity, specific humidity, is 100% saturated with water. Now, here's a question for you all. How do you cool down the air? How do you cool down the air to get it to reach the dew point? So, probably a lot of you are thinking, well, maybe, at nighttime it starts to get cold. And that's true, right? That cools down the air, and that's why a lot of times we get fog in the morning. We get, how the fog burns off once it gets warmer in the day often. But a lot of times we have fog in the morning. We get dew on the grass in the morning. So that's one way to cool down the air and make a cloud or make precipitation or make dew. But there's another way that's very common, and it's very weird, but it's a very, very common way of making air reach its dew point. Now, this is a little bit weird, like I said, but this is true. As gas depressurizes, it also cools. As gas depressurizes, it also cools. So, have any of you ever taken like an aerosol bottle like this of hairspray, or maybe you take, one thing that works really well is if any of you have any of those compressed air cans that you use to clean electronics, you take that, you spray it for a while, you'll notice that the aerosol can starts to get very, very cold. So this will start to get very cold. I remember when I was a kid, my sister, I grew up in the 80s, so it was like my sister, they had big hair. Hairspray, a lot of hairspray, and the big hair. My sister always had like a lot of hairspray. And I would always she'd spray and spray and spray and spray and spray the hairspray. And then I would grab the hairspray bottle and be like, it's cold. I used to wonder about that when I was a kid. Is the hairspray cold? No, the hairspray's not cold. It's not that the hairspray's cold. It's that when you depressurize this condensed air, it's condensed and compressed. When you release the pressure, it expands and it depressurizes. And that's what causes it to cool. Okay? Any gas depressurizes, it will cool down. That's, by the way, how air conditioners work as well. You might know that in an air conditioner, there's a compressor. Okay, it's compressing the gas, and then it releases it, and that's what cools down the air in order to cool your house down. Okay, so guess what? You learned in the last lecture that as you move up, up, up in elevation, so we're going to go up, 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 up in elevation this way. Oh, I'm sorry, this way. Not reading this right, am I? We're going to go up, 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 up in elevation. You'll notice that the pressure plummets. Okay, so as you go up in elevation, you go down in pressure. So guess what? When you go up in elevation, you depressurize the gas. As the air rises up through the atmosphere, it decompresses, and therefore it cools down. And eventually it will cool down and reach the dew point. So the rate, oh boy, here we're getting into some of the most difficult concepts, I'd say, in the whole class. So again, whatever you're doing, put it down, concentrate on this. This is hard stuff. So you got to now learn a little bit between the Waller and the dollar. Okay? So I'm going to introduce to you now the Waller and the dollar, and you have to know the difference. So what's the Waller and the dollar? There's this thing, called a lapse rate. That is change in temperature over the change in elevation or altitude. Okay. So as we go up in altitude, what happens? Pressure goes down. Okay, this is P with a down arrow, so it means pressure goes down. And as pressure goes down, if you have a parcel of air, it's going to rise and it's going to expand. Why does it expand? It expands because pressure is going down. Pressure is going down. Pressure is going down. So as pressure goes down, it depressurizes, it expands, and it cools. So you can notice this parcel of air is getting fatter and fatter and fatter. The pressure is going down. It's depressurizing. It's cooling down. Okay? And as it depressurizes, it cools. It cools and cools and cools. Okay, so you start off at 10 degrees Celsius. By 2,000 meters, you go up 1,000 meters. You cool down 10 degrees. You go up another 1,000 meters. You cool down another 10 degrees. You go up another 1,000 meters. You cool down another 10 degrees. So that is called the adiabatic lapse rate. So adiabatic lapse rate, that's a weird word, right? Adiabatic. Adiabatic means kind of equal energy. Okay, so there's no change in the energy. I know this is like gets into deep thermodynamics. You don't have to understand it, but you do need to know that adiabatic lapse rate is the change in the temperature with the change in the elevation. Okay, change in temperature with change in the elevation due to decompression. Okay, so we go down 10 degrees minus 10 degrees Celsius per 1,000 meters. That is the adiabatic lapse rate when the air is dry. Okay, so in other words, the dry adiabatic lapse rate. To abbreviate, we call it DALR, or the dollar. Okay, so that's the dollar. It is, again, it is the change in the temperature with the change in elevation due to depressurization when the air is dry. That's the adiabatic lapse rate. Okay. On the flip side, there's the Waller, which is the wet adiabatic lapse rate. Okay, I'm going to put the wet ALR. Okay, so that's the dollar, and then this is the Waller. Okay, the wet adiabatic lapse rate is only 6 degrees per 1,000 meters, so it does not cool down as fast as the dry adiabatic lapse rate. So why does it not cool down so fast? The reason that it doesn't cool down so... Oh, sorry. I think I got someone at my door. Hold on a second. I'm going to stop this. Hi, everyone. I'm back. Sorry for the interruption. My daughter was at the door. So anyway, oh, actually, I was on the next slide, wasn't I? So, oh, yeah, I was here. Oh, no. Yeah, I was here. Okay. So, okay, another angle to this is how is the density of cold air compared to hot air? So that's another topic we have to explore. So this is a graph showing density here on the vertical axis, temperature here on the horizontal axis. You'll notice that as temperature goes up, right, so we're increasing in temperature going this way to the right. You'll notice that density goes down. Okay, so what that means is that warm air is less dense than cold air, and less dense air, remember, will always rise. Okay, so due to buoyant force. So this is what you have, is that when air warms up, that air will rise. Okay, when it rises, it's going to cool down. Okay, and eventually it's going to cool down. So it's rising, and as it rises, it gets cooler and cooler and cooler until it gets so cool that it reaches the dew point, and then you get condensation. That's how you get clouds, nice fluffy clouds form. Okay, so that's kind of the story of how you get clouds. Has a lot to do with, as I said, the adiabatic lapse rate, the dry and wet adiabatic lapse rate. Oh, and that's one thing. Oh, I totally forgot to mention this, actually. Here, let me go back to this graph. So you'll notice that we have the dry adiabatic lapse rate here. Okay. Now, when your air, right, is rising, and it hits the dew point, it starts to condense out. You start to get cloud formation. What's going to happen? So as it condenses out, you're going to have the water vapor condensing. And what that's going to do is, remember, when you have condensation, you have also the release of latent heat. Okay, you all remember that? I mean, it was like way back we talked about, I'm going to go all the way back here, right? It's this stuff. Remember this? So way back at the beginning we talked about this. So remember, when we go from water vapor to water, we condense, and that's going to release some heat into the atmosphere. Okay, that releases heat. So what do we have? Let me kind of zoom back to where we were here. This is what happens. As this condensation occurs, it releases that heat, releases latent heat. And that release of latent heat offsets adiabatic cooling. So it offsets the dry adiabatic lapse rate. And so it's going to be cooling at only 6 degrees per 1,000 meters because that release of latent heat offsets the adiabatic cooling. Okay? So what you have is a smaller adiabatic lapse rate because of the offset from condensation. So we call this the wet adiabatic lapse rate. Okay. So anyway, the whole story really of getting clouds to form and getting weather to form then is just a matter of getting air to rise. Because if you get air to rise, it will eventually reach the dew point, and you will get condensation and precipitation. So how do you get air to rise? This is how you get air to rise. There are several ways, and we're going to go through the different ways. One way is convection, right? So just normal convective currents where you have the sun is heating up the earth, right? Here's the solar radiation coming in. It heats up the earth. The air near the earth gets hot. It starts to rise buoyantly because it's warm, right? And warm air is less dense. So that's one way you can get air to rise and start to condense and form clouds, okay? Another way is through topographic effects. A really famous one being what's called the orographic effect, or the oro, by the way, means mountain. So this is kind of like what might be called a mountain lifting, okay? So mountains, as air rises and passes over a mountain, it's going to rise up and it's going to depressurize. That's going to cause the air to cool down and condense, and you're going to get rain on one side of the mountain. So this is very common to find in mountain ranges. You have one side of the mountain that's lush and green and gets lots of rain, and the other side is actually bone dry. So what happens, if I could take you through this process, the moist air approaches the mountain and starts to lift up. As it goes over the mountain, it cools down, it condenses, it hits the dew point and releases all of this rain. And then when it crosses to the other side, it's now totally dry. It's bone dry air because it's precipitated out all its moisture. It's going to sink down this way, and as it descends, it's going to heat up and dry out. So just like rising air cools down, sinking air is going to heat up. Okay, so that dry air is going to heat up and descend. It's going to get hot, and you're going to have hot, dry air on the other side of this. And that creates what are called rain shadow deserts. Okay, some of the driest places on Earth, the Atacama Desert, is a rain shadow desert like this on the other side of the Andes Mountains. Okay, a very, very, very common way that air rises and creates weather and precipitation is when you have a cold air front move in. So when cold air comes, cold air is more dense. It hugs the ground. So this cold air will roll into a place with relatively warmer air. So think about like when a cold front rolls in from the north here in Corpus Christi, okay, or maybe rolls in from the west or whatever. But it comes in and it wedges. It's called frontal wedging. it's like a wedge, and it lifts up the warmer air. It causes that warmer, moister air to condense, and you start getting sometimes really violent storms. Okay. Another way is convergence, where you have two air masses meeting together. And when you have two fronts coming together, two air flows coming together, they converge, and there's no direction for it to go except for up. So that's another way. And it creates a low pressure system, and you get this, precipitation weather. Okay. So this kind of gets to the topic of atmospheric stability. Atmospheric stability refers to how much vertical movement of air there is in the air column. So let's talk about these things. It's the idea of stability of the air. So, less stable air will tend to stay at the same altitude and resist vertical movement. While so that's stable air. Stable air will stay at the same altitude, whereas unstable air is going to want to rise. Okay, so this is what happens when you have air that is colder relative to the air around it. So let's say you have a parcel of air that's relatively cooler compared to the air around. It will stay at the same elevation, right? It's not going to want to rise uncontrollably because it's colder. It's going to be more dense. It's going to want to sink. On the other hand, if you have a parcel of air that is hotter than the surrounding air, once it starts rising, it's going to just keep rising. And it's just going to keep rising, 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 and it's not going to stop. It's unstable. Okay? That creates these what's called vertical movement of the air. So air is rising, and there's a lot of vertical movement up and down through the air column. Okay, this creates some of the most violent weather that we know. So violent weather storms, including hurricanes, happen when you have unstable air like that. So again, this is all tied to this all important idea of a lapse rate. Okay. So sorry, excuse me. Oh, went down the wrong tube. Sorry. So the whole idea of, if you could imagine here, what's going to make this stable versus unstable? So when you have hot air, it's going to start to rise, but it's also going to start to cool adiabatically, right? It's going to start cooling according to the Waller. Okay. And the reason that it's cooling here according to the Waller is because you can see that condensation is simultaneously taking place. So it's going to start cooling down. So this air is cooling. So this hotter air is cooling down as it rises. So the question is, this cold air is also getting cooler, though, as you rise through the air as well. So the question is, what's going to cool down faster, this parcel of air or this air? So that's what's really going to ultimately determine atmospheric stability. Okay, it's actually what it's going to be is something called the environmental lapse rate versus the Waller or the Dollar. Okay, the dry adiabatic lapse rate or the wet adiabatic lapse rate. So I know this stuff is really complicated. I really highly suggest that if you have a book, you read through this stuff carefully in your book, because it's definitely the hardest part, I think, of this class is all this stuff about adiabatic lapse rates in weather. So we got to talk about this yet another type of lapse rate. Okay, so we've talked about the Waller, we've talked about the Dollar. Now we need to talk about the there's no real good word for this, but the ELR. Okay, the environmental lapse rate. So environmental lapse rate means, it's very simply, it's kind of funny. This is actually one of the easiest lapse rates to understand, but students have the most trouble understanding it. All the environmental lapse rate is simply the rate at which the atmosphere cools down with altitude. Okay. So it's if you can imagine sending up a weather balloon, you're going to have your weather balloon here. Okay. It's going to have a thermometer, and that weather balloon is going to go up, and it's going to measure the temperature here, and temperature here, and temperature here, and temperature here, and it's going to be cooling down. Maybe here it's 10 degrees. Maybe here it's just maybe it's 9 degrees here. Maybe it's 8 degrees here, 7 degrees here, And it's just going to cool down as you go up in the air. And that rate of change is going to be, the change in temperature with the change in altitude is simply going to be the environmental lapse rate. Okay? Now, you might be wondering, well, what's the difference between that and the adiabatic lapse rate? Well, the adiabatic lapse rates never change. Okay? Adiabatic lapse rates are thermodynamic properties of air. Okay? Air is going to cool down always 10 degrees Celsius per 1,000 meters if it's dry. If there's condensation occurring, it's going to be, then it can change. It depends how much humidity is in the air, but it can be anywhere between 5 degrees Celsius per 1,000 meters or 10 degrees Celsius per 1,000 meters. So environmental lapse rate, however, depends on nothing else but the weather. It's just whatever the weather is doing that day, and whatever it is, the change in temperature with the change in altitude, that's what environmental lapse rate is. So the lapse rate is the rate at which temperature of the atmosphere decreases with the altitude. Okay? The lapse rate tells us how much the temperature is decreasing the higher in the air we get, and the higher you are in the atmosphere, generally speaking, the colder it will be. That's not always true, but it's nearly always true. Okay? So we have three kinds of lapse rates. Environmental lapse rate. This is maybe the average environmental lapse rate is maybe around 6.5 degrees Celsius per 1,000 meters, but it can change. It can vary. It depends on what the weather is doing that day. Okay, if you have it just depends. The dry adiabatic lapse rate is always 10 degrees Celsius per 1,000 meters. It depends on nothing but just the plain thermodynamic properties of the air. Okay? So it doesn't change day to day. It's always the same. The Waller is anywhere between 6 to 10 degrees Celsius per 1,000 meters. The reason that it varies, and by the way, I think this is a homework lecture assignment question. The reason that the Waller can vary is it depends on the specific humidity of the parcel of air. If the parcel of air is almost bone dry, you're going to have a Waller pretty close to the dollar because it's almost dry. If you have very moist air, then you're going to, with a very high specific humidity, you're going to get a more pronounced offset effect that's going to cause it to be more like 5 degrees Celsius per 1,000 meters. Okay, so it depends on what the humidity, the specific humidity of the parcel of air is. That's why there are differences in the wet adiabatic lapse rate. So we have these, back to this idea of stability of the air, okay? Because it plays a huge role in what kind of weather we get. What is the stability of the air, okay? We have this condition called absolute stability. Absolute stability occurs when the environmental lapse rate is less than the wet adiabatic lapse rate. So what that means is that as the air cools, as a parcel of air rises and cools, it's always going to cool down faster than the surrounding air. So it's always going to be getting colder, faster, and be cooler than the surrounding air. Because it gets cooler than the surrounding air, it's not going to want to rise. You see what I mean? Because if it's cooler than the surrounding air, if a parcel of air cools down faster and it's cooler than the surrounding air, it will always be colder than the surrounding air and it's going to sink. Okay, it's going to want to sink and not rise. So this is what that graph would look like, right? The wet adiabatic. So as this parcel of air rises, it's always going to rise. Remember, a parcel of air is going to rise along the adiabatic lapse rates. It's going to cool according to the adiabatic lapse rates, either the dry or the wet. It's not going to cool according to the environmental lapse rate. Okay, the environmental lapse rate just gives you the change in the temperature of the surrounding air with temperature with altitude on a particular day. Okay, so as this parcel of air rises, it's going to change in temperature according to the adiabatic lapse rates. So environmental lapse rate, when it's less than the wet adiabatic lapse rate, that means that the surrounding air will always be cooler than the rising parcel of air with height. Okay? Absolute instability is the opposite. It's when the ELR is greater than even the DALR. And so that means that as the air rises, it's going to follow the dry adiabatic lapse rate, and it'll always be warmer than. See, we have temperature here on the bottom axis. It's always going to be to the right of the purple ELR line. So this is the ELR right here. Notice how as we rise along the adiabatic lapse rate lines, we're always to the right of the ELR. That means we're always going to be hotter than the surrounding air, and that means our rising air is going to rise uncontrollably. Okay, it's going to just rise and rise and rise and rise and rise, and that's what creates unstable air. Okay, so conditional stability is when basically the ELR is between the DALR and the WALR. Okay, so at a certain point, you'll notice here, at a certain point when we're rising, we're going to reach a point where it's absolutely unstable, or it is unstable above a certain altitude. So in this case, you can see the ELR crosses the dry and wet adiabatic lapse rates. Okay, so that's when you have conditional instability. So when you have stable air, this is what a day with stable air looks like. And you've probably seen days like this, Corpus, all the time. You know, it's you know, low-lying clouds, drizzle maybe, gentle weather, no thunderstorms, just kind of wet, drizzly weather. That's stable air, okay? This is what unstable air looks like. There's vertical movement of the air, okay? And that means you can see these thunderheads developing. Sometimes these things, I've seen these, like you can actually see these clouds, you know, getting taller and taller by the second. And this creates violent weather. Cumulus clouds, thunderstorms, cyclones, hail, you name it. That forms with unstable air masses. So condensation, I want to make this clear. Condensation is you know, what you get once air reaches the dew point, but that is not the same as precipitation, okay? Precipitation is a little bit different, okay? In order for precipitation to occur, droplets have to kind of group together and become large enough to actually overcome air resistance to fall. So important basics of cloud formation. Clouds are made of tiny microscopic droplets of water, okay? They are so tiny that they are suspended in air. They can't fall because they can't overcome air resistance. They form from condensation of water vapor from the atmosphere. Condensation occurs when air reaches the dew point. This is all review. I've said this a million times in this lecture so far. So to condense and form clouds, water vapor also needs another thing called condensation nuclei. So, excuse me, in order to actually get condensation to occur, I know this sounds kind of funny, but water can't just condense into empty space. It needs to have a surface to condense onto. Usually what that condenses onto are aerosols. So remember, aerosols are solid particles that are floating in the atmosphere. It's like smoke, pollution, could be sea salt, it could be dust, whatever. But in order for condensation to occur, you need to have condensation nuclei. So you probably have heard in your life about cloud seeding. So sometimes airplanes, in order to encourage rainfall to occur, airplanes will actually drop aerosols into the atmosphere to give condensation nuclei for condensation to occur and to generate rain clouds. So that's called cloud seeding. Okay. A little bit more about clouds, certain types of clouds, right? We have, I don't want to get too much into this stuff, but you know, we have high clouds like cirrus clouds or cirrocumulus. Cumulus kind of means the same as a cumulate, right? They're kind of clumpy clouds. Whenever you see cumulus, that's kind of the puffy type clouds, okay? So high clouds consists of cirrus or cirrocumulus. Now these are actually mostly made out of ice crystals at high altitude. Now remember that high altitude, water vapor is very scarce. It's very, very cold. Remember that cold air can't hold very much water, and so water vapor is scarce, so clouds are usually very thin at high altitudes, okay? So you usually have very thin clouds made of ice crystals. Middle clouds between 2,000 to 6,000 meters get altocumulus, altostratus. Stratus comes from layer, so it's like a layer of clouds. Cumulus again, I mean cumulate, like a accumulation, like a puffy cloud. Okay, so these are just sort of accompanied by infrequent light snow or drizzle. Now these are the clouds where you start to see more weather. So stratus, nimbostratus. Whenever you see nimbo refers to rain. So these are kind of like gentle drizzle type clouds. Nimbostratus, these form in stable air. Stratus, these low-lying kind of level clouds. Stratocumulus comes with these low-lying cumulus clouds. Okay. Now these are the clouds that really bring violent weather. So cumulonimbus are basically thunderstorm clouds. So these are the big puffy clouds that are occurring over a large range of altitudes. So they start off low, but because there's vertical movement of the air, they're going up to higher altitudes. Cumulus clouds are these nice little puffy clouds you get on fair weather days. Okay, so yeah, a little bit more going with precipitation coming from the clouds. So just you might be interested to know that the rainiest place on Earth is in India. This I don't actually know how to even say this name, Wasiranam, India. So wettest place on Earth. And actually, I was kind of surprised at this. The snowiest place on Earth is actually in Japan. Does that surprise you? I was like, wow. I thought it would be, I don't know, Canada or something like that, but it's actually in Japan. So precipitation, though, is water falling to Earth, and it could be either liquid or solid, okay? So rain, or it could be snow, ice, or hail. Okay, all that counts as precipitation. So in order to have precipitation occur, you have to have first condensation, but it's not enough to have condensation. You have to have the condensed water droplets and clouds get large enough to actually overcome air resistance and fall. So there's two ways of doing that. There's something called coalescence, so collision and coalescence. This happens mostly at low latitudes in the tropics. Little water droplets simply collide, they get larger, and they fall. The second process is called the Bergeron process. The Bergeron process happens more at mid-latitudes, so around here in Corpus Christi, included in this. Bergeron process is when you have the formation, actually the deposition. Remember deposition? Deposition refers to going directly from a gas to a solid. So you have the deposition of ice crystals at high altitudes, and actually these ice crystals grow. They get larger and larger and larger until they finally overcome the effects of gravity, effects of air resistance, and they start to fall. And as they fall, they get warmer and they melt, and that's what generates the rain. And so actually a lot of the rainfall that we experience in Corpus Christi actually starts off from the Bergeron process, because it's at more of a mid-latitude process. So precipitation comes in a lot of different forms, right? By the way, we're very close to being finished here. Rain, snow is crystallized. It's nice. That nice fluffy snow is like crystallized H2O, right? You can also have sleet, glaze, freezing rain, and of course hail. The way that hail forms, I'm not going to go over, there's so many different types of precipitation. I don't want to go into all the details of how it forms, but I do want to explain a little bit about hail. Hail is kind of interesting. So hail forms when you have very strong thunderstorms, very strong vertical movement of air. So what happens is that the pieces of ice, pellets of ice, start to get heavy enough to finally fall, but as they fall, they're blown back up by these very strong vertical currents of air. So they're blown back up, and when they get blown back up, they grow larger. And they get larger, they start to fall again. And when they fall, they get blown back up until finally they get so large that they overcome the effect of those vertical currents of air, and they fall. So when you see very large hailstones, it can be, that basically means that there are very strong currents, vertical currents of air. One thing I actually just found that's out, a few days ago is that hail actually, there have been people, killed actually by large hailstorms. So it does happen. I was actually reading about a hailstorm that occurred in the 1800s that caught like a country fair, about all these people outdoors without any cover, and it killed like 240 people or something like that. So it's amazing that it could be that deadly. But anyway, we do get some hail here once in a while in Corpus. But anyway, I think that's all I have for you today. So hope you enjoyed the lecture. I will talk to you next week. Until then, I will say adieu.